My name is Nathaniel Sable, and I will be teaching you part 2 of kinematics. You've already learned the 3 main types of kinematics, and I'll be going through it to teach you how to use those on Matlab. For example, how to solve kinematics equations in Matlab, as well as how to apply them to your data sets and use them in modeling endeavors, so that when you're doing predictions, they'll be far more accurate using the kinematics you've already learned. So we're going to be referencing this article a lot, modeling of chlorine decay in drinking water supply systems using Epanit MSX. I'm not sure if I'm pronouncing that tool correctly, but I'm giving it my best shot. But this article is another one that analyzes chlorine decay in pipes and how it's distributed. And it also gives us our central equation to the right. dc over dt equals negative kb times c to the n. And you'll notice this is c to the n, not c to the 0, not c to the 1, not c to the 2. So this isn't exactly one of our kinematics equations that we've seen before, but it's more saying we don't know which one to use in this case. Why does this matter, you ask? Well, if you don't think it does, tell me what plot best fits this data here. Because we see they've tried fitting it with a 0 order one, but that goes straight through it. But still, can you tell me with certainty if this is a second order or a first order? Will it slowly approach something, or are these two just slight outliers and it'll just keep on decreasing closer and closer to 0? From looking at it, I'm not sure I can tell, and I can guarantee no one can tell you accurately in the future. But this is an important question because, as I said, a second order equation will approach one number far in the future. A first order will keep decreasing until near 0 or keep increasing until near infinity, unless there's other things to stop it that make the equation more complex. And this is something important to be figured out and something that we need to solve. So how do we figure out whether it's 0, first, or second order? The answer is, drum roll please, linearization. This is the same data in both the graphs above, except in one version, it's in its pure raw form. In the other one, it's gone through a process called linearization, where we modify the data slightly. I know whenever I say modifying the data, it sounds like I'm cheapening it, but this is a simple modification, like double all the data or square all the data. It may change it, but it changes it uniformly, and it can easily be changed back for every point. So that's what linearization does. It's a consistent change over all the points designed to alter the data and put it in a linear form so that we can observe it and hopefully figure out what the equation for it is from backtracking. So again, let's go over the kinematics you know so far. 0th order, that's just a linear function. You've been seeing these since elementary school, I assume. Maybe middle school. My memories of my previous schooling before high school are a little bit blurry, so I honestly have no idea when that's first established. First order is the exponential equation I've seen before, n times a constant. And second order, a lot of stuff under a constant. And let's look at it in its linearized form. Well, we've already had the linearized form for 0, so linearized form I should say for first order and for second order. And this is a simple transformation. It's just taking the log of y and the log of x. That means that k and x will be moved to just moved it down to normal level, and we'd have to take the constant that was out there as the logarithmic form. But this just gives us our variable answer, albeit with some transformation, our x, a constant, plus another constant. And these can easily be transformed back. Same with second order. You have 1 over all the answers minus your 1 over constant and your constant times x. And this is actually how it's transformed, because if you look at it in second order, you can just divide both top and bottom by yo, and you'll get kx minus y over 1o. And then when you just divide everything by y and multiply everything by what's under here, this is exactly what you get. So let's move over to some Matlab examples over here. And just in case you didn't believe me earlier when I said it, these can all these things here can run they can solve your ODEs for you. And as you see, we have 0th order, 1st order, and 2nd order. How do these work, you ask? Well, it starts with the symbols line. This is to establish what variables we'll be using. You can, in one quick little block, establish what will be your independent and your dependent variables. By just having the dependent and the parentheses around independent, it'll automatically show that those two are related and that X will be the basis of change for it. You can also establish as many constants as you want, your initial variables and your K. After that, you do an equation. You state that this equation will be a differential of your dependent variable and your independent variable. And you set equal to it, be it 0 order with just K, 1st order with 1y, or 2nd order with y squared. You add a condition into it, basically saying when X is equal to 0, your y value will be equal to your y initial. And then you throw it into dsolve, referencing both your equation and condition. And it'll spit out a formula for you. Now, normally you would use this y somewhere else and put this here, I put a semicolon here to stop it from outputting, but we do want you to see the output. So let's move on to a quick example of linearization. If you look here at this data, you'll notice that our time data is neat and clean, and our A data is about as far as from neat and clean as you can get, though you can tell it's decreasing somehow. I will tell you right now that this is an example of some chlorine decay, where the concentration is going down over the 5 time intervals. But what order is chlorine decay? I'm sure some of you remember it from the last exam, but please hold your answers until after I show you how we would solve this. So the best way to do it would be to transform the data, leaving it untransformed for 0, log of the output data for 1, and 1 over the output data for 2nd order. And you can run that through a fit function with set the polynomial 1 here. And this would spit out your answers, your equation answers here, and tell you how good a fit is in B. So we can run that. And you get a lot of stuff to go through. But as you can see, it's separated out into information about how well the line fits here, SSE, R squared, and your linear model here. But that's a lot to read through, and just a quick, you could do it if you really want to, or you don't remember this trick I'm about to show you, but a quick, easier way is to go into the variable that is holding the information about how well it fits, put dot R squared, and if you have some MATLAB, then this will give you a quick prompt to help you fill it out, and run again. And you can just spit out the answers for what the R squared value is. So of these linear functions, 2 of them are high 0.7, decent fit, but 1 of them is an exact fit. This shows us that chlorine decay, as we knew before, is a 1st order decay reaction, and it is perfectly fit by a linear model. And what do we do next with that? Well, we've linearized it. We've been able to find M1 now contains the values for how we can linearize that data if we want the log of it. But if we want the actual concentration over time, well then, let's move on to our next part. So here again, we are going to solve the 1st order kinematics equation. Yeah, sorry about that. But now we're going to go a little bit farther. We are going to replace these constant variables with actual numbers. And to do that, we use the subs function. So to use the subs function, you first need to know what equation do you want to deal with, in this case, y. What variables do you want to deal with? And in these little curly brackets, or I guess wavy brackets would be the best way to describe them. You plug in our k constant and then our y0 constant, and then you plug in the replacements for them. Because if you go back here, you will see that k remains unchanged, but currently what we have right now in our b plot, or our constant near x, is the log of y0, not y0 itself. So while you can just plug in p1 for k, you need to take the exponential version, or raise to the x, the p2 we got. And by doing that, you will find that MATLAB likes to make things overly complicated. I don't know how to stop it. I don't know how to change it. I just know it happens. But if you want to double check what the values are, it will be a y0 out front of 10.023 and a k value of -1, which does fit with what we know about chlorine decaying constantly. And if you check, you'll notice that the number on top and on bottom are very similar in each case, though this one is about 10 times larger. So that does fit with what we're seeing. And if we go and try to plot it by just removing these, we will find that it is an extremely good fit. A perfect fit, you could say. Whenever it decides to load, I gave it a perfect intro and it never loads for me. I'm grateful. Well, what are you gonna do? All right, and there it is. So you can see we have perfectly matched our chlorine decay function. Now let's look more at our specific article and how it applied this. So the modeling of chlorine decay in drinking water supply systems article that we used, it measures water going through a pipe that is 27 kilometers long. For us in the United States who hate our conversions, that's a bit over, that is a decent amount over 15 miles. And it also has 6 exit points where the water is drawn. So all across here. And this chlorine is often used after treatment, not because there's someone out there who likes the taste for some reason, but because there's bacteria everywhere in the world. So after the water is treated at the treatment center and sent out, there needs to be something in it to stop natural organic matter, or NOM, from being activated in things like diseases or bacteria and infecting the water all over again after it was cleaned. And in most cases, that's chlorine. So, but you also want to keep this level at a perfect match to it. You don't want to have too much chlorine when it reaches the end. Otherwise, people are going to complain about drinking pool water. Sorry, I keep losing my train of thought. But you also don't want to have too little, because then they might be at the hospital complaining about sore stomachs from that NOM that got into their system. And in our particular case study, when they plotted it, they found it was a little bit off. And I should say again that this is a different type of linearization. In this case, you don't transform the outputs at all, you just graph it against something else. So in this case, it is their theoretical concentration graphed against what they have observed. So by matching it up, they will see, is this a perfect one-for-one match, or is there something off? And as we can see here, their data has something off in first order, nth order, and second order. So they tested in all of them, and none of them have really given them a very decent match, so there's more to be asked. In this case, they missed this, which is called a biofilm. And that does look nasty because it is. Biofilms are something that naturally happens because when that chlorine breaks down the natural organic matter in order to keep us safe, that natural organic matter starts to settle on the sides of the pipe. And that leaves a lot of nutrients for new bacteria to grow. So again, leads to a new reason that we need the chlorine in there. It's something that there's a lot of interesting work to try and clean it or deal with it, but it's just another factor on the inside of pipes that you have to think about when wondering where is the chlorine being used to deactivate. And this is the answer. So once they've added in that, modifying their kinematics equation appropriately, they were able to match up all of their orders to it. Now, this would likely require that you change your ODE in order to make this adjustment, but that's not something we're requiring of you at this point. But it is something to be aware of in the future. You can ignore it for now, but be ready for it. And it's going to be something useful. So now that we're on to closing remarks, I think I already said them on the last page, but yeah. So you've learned this modeling technique, and I'm hopeful you'll be able to use it more in the future. For the full citation, see here, and you have your quiz. I hope that everything you learned here today was helpful for you, and I thank you all for listening to me ramble and try and teach.